All right, this recording is going to talk about what we call parametric equations. Now, to understand parametric equations, we have to understand why we would look at things just a little bit differently. So the problem here on the screen is one that discusses basically vertical motion. So if we launched an object at about a 45-degree angle with an initial velocity of 48 feet per second, this model up top should model that object. So it's flying through the air along that path. Now, one thing we already can't really see is the direction of the path. But again, we kind of assume that if, again, we're starting at x equals 0 and y is sort of moving along as we go, we usually assume our starting point, again, right around that origin position. But again, not necessarily stated. What is the maximum height of the ball? Well, again, from what's labeled on our screen, we know that the vertex maxes out at 18 here, so I would assume that's 18 feet. How far is the ball from the starting point when it hits the ground? Well, again, it's labeled for us here at 72 feet. So we have that answer there. One thing we can't answer, again, going back to that idea of time, is how many seconds did the ball take to reach maximum height, right? Or how many seconds did it take to reach the ground? How long did it take to get to these 2 points along the way? We can talk about the distance from the start. We can talk about the height from the ground. But again, we're not really illustrating the time, even though they mention that it's traveling at 48 feet per second when it's initially launched. Again, a question we can't really answer with just the two-dimensional, or what we often call a rectangular equation, just talking x and y. So instead, we can use what's called a parameter. A parameter is sort of a third variable that kind of governs what the first two variables do. And it will construct for us what we call a plane curve. A curve that travels through that two-dimensional plane. Now, in plotting that graph, the nice part about a parametric equation, or a set of parametric equations, is that it will show orientation, or it will basically show the direction. Again, parametric equations have direction, and it'll also show the t-values, as we say. T, again, being that third variable, or the parameter. So over here at the left, we have a different set of equations. Now, you'll notice we have two of them. X is going to be equal to 24 times t, the time, root 2. And the y coordinates will be governed by this expression here, negative 16t squared plus 24t root 2. So if we take just a second and we plug these t values into our equation, right, when we plug in 0, right, you've got 0 right here. Again, 0 times 24 root 2 would be 0. And 0 times squared times here, and plugging in 0 at the bottom, we get 0, 0 for x and y. We plug in 1 for all the t's. Again, we're going to get all of our x values separate from our y values, and then we can plot those points, right, on the graph over here. Now you'll notice that t equals 3, though x would have been 101, so it should have been right over here, we also ended up with a negative y value. So essentially that would be after we've already passed the ground or hit the ground. But again, after that, we could go ahead and graph a line through those points. All right, so I threw a line on there. Now you'll notice, again, that line's not exactly perfect. It would probably help to have more t values. Maybe instead of going 0, 1, 2, 3, I should have plotted every quarter second or at least half a second. I would have gotten some more points on my screen. What I do know, though, is that this line has a direction. Again, it's going to travel. Oops, sorry, I didn't mean to move it there. It's going to travel in this direction. So again, for parametric equations, we often note the direction using an arrow. And notice I've also labeled the points according to what t-values they were. According to those t-values. Move that over just a little bit there. So we know that we've got that 1 here. Again, we also know we technically probably should have gone up and reached that 18 from the previous screen. We know we got 18 feet high. But again, we're kind of traveling along that route. So again, parametric equations show the time, they show the direction, they show a lot of extra information compared to just rectangular graphs. And really it just takes plugging some t-values, plug those parameters into your parametric equations. Para, again, pair of equations, kind of an easy way to think of it. Get your x values, your y values, plot x and y. We're still plotting on a rectangular plane, right, x and y, but we also want to note those t-values, right? How did we break up our equation as well? I often think of it as graphing. If you're familiar with the old Etch-a-Sketch, if you want to move around the screen, you've got to move both the x values and the y values. You can't just travel one directionally and have it determine where it goes. We determine both x, left and right, and y, according to sort of a third parameter. Now on your calculator, we can set your calculator to parametric mode. So you'll notice here at the top, if you're on your mode screen, instead of function, we could call it parametric. That means that when we go to our y equals or our function button, it'll have x and y. So x1, y1, x2, y2. We can do lots of different parametric equations. But again, we need an x and a y for one equation or one set of equations. Also, when you type that xt theta n button, it's just kitty corner to your second button. If that's what you normally use to type in x, which it should be, now it will magically, since we're in parametric mode, it will say t instead. So you'll notice you get that xt theta n. X is when we're in function mode. T is when we're in parametric mode. So you can still use that same button, just don't be surprised when that different variable pops up. With that same idea, once we're in parametric mode, if you go to your window, you can put in where you want to start your t-values, where you want to end your t-values, and what you want to count by for t-values. Remember I talked about if we'd put more points on our screen, our line on the previous page would have been a little bit clearer. So it might not be a bad idea to make that fairly small to get lots of points, right? The more points we have, the more accurate we'll graph. So it's always a good idea to have a tiny t-step. However, the smaller that you go, if you make it too small, that can also take your calculator a lot of time to graph. So you want to be fairly reasonable. Again, our x's and mins and maxes and scale, y min max and scale, they'll determine again our screen. But the t-step, the t-min and max, also very important sometimes. And then finally, if you hit graph after that, again, sometimes you get those graphs that come out. This would have been the one that was kind of programmed in there on the previous screen. You'll notice it starts and it stops. Because remember, we're putting in the t-value at t equals 0. We're also putting in when we stopped. So on the previous screen was 3.2. So it's not going to just infinitely graph forever. It's only going to graph what you tell it to graph. So just be careful there. If you want to trace along there, the nice part is it will tell you not only the x and y values, it'll also tell you which t-value you're at on the graph. And you can even type in those t-values. Once you press trace, you can press whatever number you want, and it will actually show you those values. Let's take a look at an example on the next screen. So let's say we wanted to graph this. Now notice we're going to go from -5 to 5, and I'm going to graph t squared minus 4 for x, t over 2 for y. So in that case, let's go ahead and go to our calculator. Now, I'm on a little bit different equation on my calculator right now. So I need to go to y equals. Again, you'll notice already in mode, I'm in parametric mode. I'm going to go to y equals screen here. Now I have my equations ready, I just need to turn that on there. So I'm going to go over to the equation, the equal sign. Turn this other one down here off. But I've got t squared minus 4, t over 2. I'm going to go to my window. And again, I'm going to count from -5 up to 5. And my t-step, well, hey, that's a distance of about 10, so how about we count by ones? It shouldn't be too bad. Hopefully that'll give us a smooth curve. If not, we can always go by something smaller. Now, thinking about my x scale, well, left to right, that could be fairly questionable. So I need to kind of figure out, well, what kind of x's might I get for answers? At 5 and at -5, this will turn to 25 minus 4 is 21. So I'm thinking my maximum probably will be about 21. I'm going to make my screen go to about 30. I'm going to give it a little extra room so we can see that fact that it stops. But if I plug in sort of in the middle ground, 0 squared minus 4 would go to -4. So at the minimum, I'm probably going to go to about -10 maybe. That sounds pretty good. And again, with all that span, maybe I'll count by 5s just for the scale, just to see what happens. Y minimum and maximum, well again, we're plugging in 5 and -5. It looks like 2.5, maybe as high or low as we go. So I'm thinking -5 to 5 might not be too bad. So let's go ahead and press graph, and we'll see what happens. So notice there's the graph that I get. Looks kind of like a parabola, because really that's what it is. Note the t squared up here for x. But notice how it stops at the ends. So one thing to note. Now, what could help us as far as graphing goes is actually looking at our numbers in our scale. So if we're looking at it again, when t was 0 over here, we would put a point there. When t is -1 or +1, we've got the same sort of values, -3, -1/2, and 3/2. So at t equals -1 and +1. I want to be at -3, 1, 2, 3, a half, and -1/2. Now let's save a little time. I threw the rest of the points on there for you. And notice what we want to do is make sure we label a lot of those. Now I'd try to label all of them, but just save a little bit of time. I noticed t = 0 was here. Again, here was 1, 2, 3, 4, and 5. And again, we've got that going on. One other thing we of course want to note is that direction. So at a few different places along the way, I'm just going to place some arrows, noting for us between the points, we're traveling from this -5 up to t = 5 in that direction. Let's take a look at a couple more examples. Again, here's one where we didn't use t, we used theta for our parameter. But notice our trig values. So we're going to count from 0 to 2 pi. Now you'll notice if we don't make the t-step the right thing, that could be a trouble. I'd use a very small t-step, and you'll notice when we plug in those numbers, we get a nice ellipse going on here. And I've even got all the t-values, all those purple dots all the way around there. But you'll notice that we went out to 3 units to the right, and again, that x value. Remember, cosine is going to range between 1 and -1. So we're going between 3 and -3, left to right. Those are the largest and smallest values we'll get. The y value, on the other hand, is using the sine. Again, goes from 1 to -1. But times 4, we could rise as high as 4, fall as far as -4. And we get a very nice looking ellipse going on there. Now, that's using a t-value or a theta, t-step of pi/12, so about 15 degrees or so. If we had used more like 90 degrees, we chop this up a little bit less. Notice what happens. Then we only find it 0, pi/2, pi, and 3 pi/2, and right back to the beginning. So we didn't get all the points in between, so your calculator didn't know what to do. It just connected the points that we found, counting by pi/2s. So that's, again, a good reason to have a fairly small t-step and smooth out that curve. The same sort of thing can happen with this one. So take a second, try typing this one into your calculator. See if you can make the graph look pretty good. And I'll reveal the answer for you here in just a minute. All right, so we've got our graph over here at the left. Again, I only counted from 1 to 4. I went in and counted by whole numbers. And you'll notice there's the graph that we got. The only thing I haven't added to the graph, again, I've got my t-values on there. But again, we always want to note that direction as well. Note that direction on our graph. Which, by the way, I think I forgot to do. Thinking back to this ellipse, we would want to somewhere along the way note for ourselves, again, the direction in which we're traveling. Even if it's a bad approximation like the one down here, we want to note that direction. So again, back to our other screen, we got our t-values, we've got enough curve to draw an accurate curve, and life looks pretty good. The last thing we want to be able to do with our parametric equations is say, well, hey, we know what they're written in parametric. They look a lot like good functions sometimes, though. Could we rewrite this as in rectangular form? And you can. The one thing you need to do in order to what we call eliminate the parameter is solve one of our equations for one of our variables, and then plug it into the equation for the other variable, essentially. So looking at this first example, what I would probably plug it in for, noticing the equation at the bottom is pretty easy to solve for t, I would go ahead and say that y equals, or 2y equals, if I multiply that 2 over, t. So now if I take my other equation, x will be equal to t, which we know is 2y minus 4. Or 2y, sorry, squared minus 4. Which means x technically equals 4y squared minus 4. And if we clean that up just a little bit, you'll see that we get the equation at the bottom. And remember that this was the graph that looked like a square root on the top, and again had the negative value on the bottom from previous. So there's where we get that plus or minus the square root of. One hint for the one on the right is take advantage of some of those trig formulas that we know. If I know cosine and sine, well, yeah, I can relate the two together using a 1. So let me fill in the work for that here in just a second. All right, so solving for the cosine and the sine, I plugged them into our Pythagorean formula, and basically it comes out as a nice equation if you're familiar with the conic section equation of an ellipse. Again, if you have any questions, make sure you talk to your teacher. Otherwise, have a great day.